Our next topic is nucleophilic acyl substitution by enolates. We'll be looking at the Claisen condensation, both self-addition as well as mixed and directed, intramolecular Claisen condensation, and using other enolates to carry out nucleophilic acyl substitution. In this video, we're starting with the Claisen condensation itself. In a few earlier chapters, we talked about reacting a nucleophile with a carbonyl-containing compound. So the nucleophile can share electrons with the carbonyl carbon, push these electrons up onto the oxygen, and that will give us this type of intermediate. Now, depending on the nature of the Y group, what happens next is going to differ. If Y is an alkyl group or a hydrogen, then that will not get kicked out, and so the O- will grab a proton from the solvent, and we end up with something like this. But if Y is some kind of leaving group, something that can stabilize a negative charge, then instead these electrons are going to come back in and kick out Y as a leaving group, so that we end up with something that looks like this. So whether we are adding a nucleophile to an aldehyde or a ketone or an acid halide or an ester, this part is basically the same, but what happens next is what differs. So for an aldehyde or ketone, we are talking about overall nucleophilic addition, whereas for an acid chloride, an anhydride, an ester, an amide, these will do overall nucleophilic acyl substitution. Now, we've looked at a number of examples, and you should recall that acid chlorides are the most reactive carboxylic acid derivative when it comes to nucleophilic acyl substitution. So this can react, for example, with an alcohol, and that will give us an intermediate that looks something like this. And then this will lead to the formation of an ester. If we have an acid chloride and we react it with an amine, we will get an intermediate that looks something like this. And then after some proton transfers and some other electron movement, we will end up with an amide. Right, so there's a number of different nucleophiles that can react. One more example that we've seen is that we can react an acid chloride or an ester with a Grignard reagent. So here we have an intermediate that looks something like this, and then this leads to another intermediate that looks like this, and a second addition will happen so that we end up with this product. So here, this part is nucleophilic acyl substitution, and then this part is nucleophilic addition. So we're going to focus on nucleophilic acyl substitution. Next, we're going to be looking at a new type of nucleophile, which would be an enolate. At the start of this chapter, we looked at aldol additions, which involves nucleophilic addition, as well as Claisen condensations, which involve nucleophilic acyl substitution. So if we have an ester, and we treat it with an alkoxide that matches the ester, followed by H3O+, we can isolate a product that looks like this. Focusing on the ester, this is the alpha-beta position, so our product is a beta-keto ester. But let's take a look at the details. So methoxide can grab off a proton from the alpha position, so that we can generate some of this enolate. But remember, the position of equilibrium lies toward the starting material, so there's plenty of ester around, which means the enolate can now act as a nucleophile, share its electrons with the carbonyl carbon, push these electrons up onto the oxygen, giving us an intermediate that looks like this. From here, these electrons can fold back in to reform the double bond, pushing away the methoxy group. That's an OCH3. And we've also kicked out some CH3O-. So here's an aspect that's different from what we saw with the aldol addition because nothing got kicked out there. But now that we have kicked this out, it is a relatively strong base, and here we have a nice set of acidic protons because they are alpha to 2 carbonyls. So another acid-base reaction is going to happen. And that will give us this intermediate. Now, before we go on, we need to think about the position of equilibrium for each of these steps. So we already mentioned that for the formation of the enolate, the equilibrium lies toward the starting material. When the enolate attacks the ester, this equilibrium still lies toward the starting material. When the tetrahedral intermediate dissociates, this equilibrium still lies toward the starting material. It's not until this last acid-base reaction that finally this equilibrium lies toward the products. And this equilibrium is so favorable that it pulls the entire reaction to this product. But this isn't the isolated product. This is still sitting in solution at equilibrium. We have lots and lots of this. And then at step 2, we add H3O+. And now the enolate can grab the proton, and we come back to this. And so our final product then is a beta-keto ester. Let's take a look at a couple of other examples. If we use methyl benzoate and we treat this with methoxide followed by H3O+, we get no reaction. That's because at the alpha position there are no hydrogens, so we cannot form an enolate. Now if we look at this third example, we have an alpha hydrogen, so methoxide can grab this off. We are going to generate some of this enolate, which can react with the ester, and that will give us some of this. Okay, but wait a minute. This equilibrium lies toward the starting material, and this equilibrium lies toward the starting material. Remember, it wasn't until we had the deprotonation of the beta-keto ester that the equilibrium was favorable. But here we don't have an alpha hydrogen that is in between both carbonyls. So there's no favorable equilibrium step, and that's why only a trace amount of this product is isolated. So it's absolutely required to have at least one alpha hydrogen, but it turns out for the reaction to work well, you need to have 2 or more alpha hydrogens. So as long as you have 2 or more alpha hydrogens, then an ester can undergo self-condensation when treated with an alkoxide base.